Welcome to this presentation in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am your narrator for today. I am David Beams, Associate Professor Emeritus of Electrical Engineering. In today's video has the subject bonus circuits. These are circuits that I thought were intriguing, possibly useful, things that might be of interest to our viewers. I thought I'll just put these out there and let you do with them what you will. First one was designed because of a request from a former colleague. He was teaching a mechatronics laboratory. He had an actuator that required a 4 to 20 milliampere current, control current input. And he had a 0 to 5 volt analog output from a data acquisition device available to do the control job with. And he asked me, how can I convert 0 to 5 volts into an output current up to 20 milliamps? And I said, we can do this. And here's the result. First stage here is a voltage to current converter, and this voltage source here represents the analog output of the data acquisition module. And we have here a 4-to-1 Wilson current mirror, and we have a cascode output stage to raise the output resistance of the overall circuit to a very high level. And here we have, this is not part of the actual circuit, that is a resistor that represents the load that's being driven by this circuit. And let me show you how it worked. This is a plot of the output current versus input controlling voltage. And the linearity and the accuracy are both impressive. And these are the benefits of the cascode stage. Works very nicely. Now, a couple of things that if you actually want to implement this circuit or duplicate it, let me point out it uses a single 15-volt power supply. Now, there is a limitation you should be aware of. The operational amplifier that you use here must include 0 volts within its common mode input voltage range. The LM324 has a rather unique property that its common mode input voltage range includes its negative supply rail. And so if we connect the negative supply rail of the op-amp to ground, then we can operate with a single supply, as we're doing here, that still includes 0 volts within the common mode range of the op-amp. If you want to use some other op-amp, you either need to make certain that the negative supply rail is within the common mode input voltage range of that op-amp, or if it's not, as is the case in most op-amps, like the old standby, the Workhorse 741, if the common mode input voltage range does not include the negative supply rail, then you need to have a negative supply voltage for your op-amp. So you could implement this circuit with 741s or a 741 in place of an LM324, but you would need to have a negative supply for that operational amplifier. Something else to point out is this thing, which I call a CYA diode. Its purpose is to prevent disaster, because it's not a question of if, but when somebody connects the battery or the power supply backwards. It's just there to make certain that nothing bad will happen when the power supply is hooked up backwards. And it's called a CYA diode because it means cover your, yep, that's exactly what it means. Okay. The second bonus circuit is a 3-terminal 5-volt DC linear voltage regulator. This is similar to what you would find inside a 3-terminal regulator like a 7805. Here we have a 4-to-1 asymmetric differential pair, a Wilson current mirror, and a voltage follower output stage. Now, one other block I'll mention here is the so-called startup circuit. It is meant to provide initial base current to this differential pair to get the entire circuit to start when power is applied, just to ensure that the circuit comes up and starts working properly. Kickstart, if you will. Okay. The load regulation is actually pretty good. The output varies from 5.05 volts at no load to 4.98 volts at 100 milliamperes. The temperature compensation is really pretty good. The output voltage with a load of 100 ohms with a 12-volt supply varies from 4.975 volts at minus 40 Celsius to 5.02 volts at plus 85 Celsius. However, I was plotting the line regulation, that is the change in output voltage with respect to the change in input voltage. And as you can see, until the input voltage gets to somewhere around 10 volts or thereabouts, it doesn't even regulate. Once it starts regulating, which it starts doing at about 10.2 volts, then the line regulation is fairly good, 45 millivolts per volt, acceptable for most applications. But that startup voltage is a little high, but we might be able to change the circuit design and improve that. And as a matter of fact, we can. If I doubled the values of R3 and R4, which are the resistors used to set the output voltage, I'll explain that in a moment, it allows the regulator to start with a lower supply voltage. The regulator is actually regulating with a 7-volt input with these new values of R3 and R4. And the line regulation is still 45 millivolts per volt. So the archive circuit will have the updated values. And if you want to go back and check the temperature coefficient and load regulation with the new resistor values, go ahead, be my guest. It's there for you to play with. Now, this is the archive circuit, and there are the new values for R3 and R4. And the archive circuit also includes an optional load current source, so you could use a constant current load instead of a load resistance. You can just set our load to a megohm, essentially take it out of the circuit and use the current source as your load. Now, I want to spend a moment talking about why this circuit is so intriguing. Okay. The output voltage of the regulator is the voltage at this common connection of all these bases, which I call V sub B, multiplied by the factor of 1 plus R3 to R4. Okay. So knowing what VB is, being able to control VB is crucial to the operation of this device. Now, the Wilson current mirror, its input side is connected to the 4 transistors, and the output side is connected to the single transistor Q5 on the other side of the asymmetric differential pair. The Wilson current mirror forces this current, or the current in Q5, to be equal to the current entering the 4 transistor side. So each of these 4 identical transistors carries 1/4 of the current. Now, the current that's flowing in transistor Q1, which should be the same as in 2, 3, and 4, is given by this formula, that the current is the so-called scale current multiplied by this factor e to the VBE1, that's VBE1 is base emitter voltage 1, divided by the thermal voltage, explain that in a moment, minus 1. The thermal voltage is Boltzmann's thermodynamic constant multiplied by absolute temperature in kelvins divided by the unit electronic charge. And if all that seems overwhelming, just remember it's 25.9 millivolts at 300 Kelvin. So with a forward bias on the base emitter junction of maybe 500 to 600 millivolts, the exponential term is obviously much larger than 1, and we can drop the 1 to a very good accuracy. We can represent the collector current as this exponential expression. Okay. Now, over here on IC5, it's the transistor is carrying 4 times the current, but the collector current in IC5 is ICE, the scale current of the transistor, which presumably is the same as the other four, because we're assuming these are all identical transistors fabricated in the same silicon die. But it's 4 times IC1. And with a little math, we find that the difference in the base emitter voltage of Q5 and the base emitter voltage of Q1, and also 2, 3, and 4, anyway, that difference is the thermal voltage times the natural logarithm of 4, which is 35.9 millivolts at 300 Kelvin. And this voltage appears, that voltage difference appears across R1. So the current flowing in R1 is this voltage divided by the value of R1. And that current is entering R2, but the same current is entering R2 through the resistor, through Q5. So the voltage VBB, as I've labeled it here, due to the two currents that join and flow together through R2, VBB is twice the ratio of R2 to R1 times the thermal voltage times the natural logarithm of 4. And then finally, the voltage V sub B, the one that we need to control, the one that we use to control the output voltage, is the base emitter voltage of transistor 5 plus the voltage developed across R2. Okay, keep all of this in mind. Here's where things get really interesting. Watch the wizardry. Okay, here's a repetition of the relationship of the output voltage to the voltage V sub B. And here's the equation again for V sub B. Now, if I differentiate the V sub B with respect to temperature, I get this expression where delta VB, delta temperature, is delta VBE5, delta temperature, plus K over Q times the natural log of 4 to R2 over R1, K being Boltzmann's thermodynamic constant and Q being the unit electronic charge. If you want to get the coefficient K over Q, you can simply divide 25.9 millivolts by 300 kelvins. Okay. And delta VBE5, delta T, there's a rule of thumb that the change in base emitter voltage of a bipolar transistor with a constant collector current is about -2 millivolts per degree Celsius. This term has a positive temperature coefficient. KT, or K over Q times the natural logarithm of 4, has a temperature coefficient of plus 120 microvolts per degree Celsius. So if I make R2 over R1, if I make that ratio right, I can make this term with a positive temperature coefficient cancel this term with a negative temperature coefficient. And a little algebra, R2 over R1 is 8.33 is the condition for temperature compensation. And it also, using these numbers for R2 and R1, that ratio of 8.33 gives me V sub B around 1.2 volts. So interestingly here, both the output voltage and its temperature compensation depend upon ratios of resistors, not the resistor's absolute value. This is key in making an integrated circuit out of this, or realizing this regulator in an integrated circuit. In an IC, it is relatively easy to make resistors with fixed ratios, but difficult to make resistors of precise values. And also by making these both the output voltage and its temperature compensation depend upon resistor ratios, as long as the resistors have the same temperature coefficients, then the ratios are automatically temperature compensated. Win-win. Okay. And if you look at the design, you'll see that actually the resistor ratio isn't quite 8.33 to 1. After some simulations, the VBE5's temperature coefficient was a little less than -2 millivolts per degree Celsius. But anyway, this was the magic of those 3-terminal integrated circuit voltage regulators. And finally, the last bonus circuit is a current feedback operational amplifier, which has an input stage where the non-inverting input has a rather high input resistance, and the inverting input has a very low input resistance, unlike an operational amplifier, in which both inputs are high resistance. And then there are a pair of Wilson current mirrors and a complementary push-pull output stage. And I have here a couple of resistors to configure the overall circuit as a non-inverting amplifier. My measurements of this circuit gives a trans resistance for this current feedback op amp of around 39,000 ohms, which is not stellar, but respectable. Okay, so let's wrap things up here. The link to these bonus circuits is in the video description. And if you find these intriguing, useful, enlightening, whatever, leave a comment, let us know. And if you don't like them, I suppose you can leave a comment and let us know. And as always, we appreciate your visiting with us. Keep those cards and letters coming. I am David Beams, and it's been my privilege to be your narrator today. And we will see you again soon in another video in the One Human Lifetime Project.